Hello, welcome back to the course of Process Control. This is the second part of Introduction to Process Control. In this session, I will tell you a brief history of process control systems. Automatic control systems can be traced back more than 2000 years ago when ancient water clocks were operated using flood regulators in Alexandria, Egypt and Baghdad, Iraq. Up to 1900, control systems were dominated by mechanical devices that could perform simple feedback functions. However, those systems were prone to instability. A stability criterion was derived independently towards the end of the 19th century by Roth in England and Hurwitz in Switzerland. The 19th century also saw the development of servo mechanisms, first for ship steering and later for stabilization and autopilots. From 1900 to 1940, electrical devices such as resistors, capacitors, and inductors that could amplify or filter signals were emerging. This period saw the modern development of feedback circuits and prompted more intensive analysis on stability problems of such circuits. Notable stability analysis was developed by Harry Nyquist in 1932 and Hendrik Bode in 1940. Despite progression of feedback circuit in telecommunication, most chemical plants were essentially run manually as the plant operators adjust material and energy flows by manipulating valves by hand. Large tanks were employed to act as buffers or switch capacities between various units in the plant. The first automated control systems were introduced in the 1920s, which used mechanical and pneumatic components to regulate processes. The period between 1935 and 1960 witnessed the introduction of mathematical models such as differential equations and Laplace transforms that could describe complex systems with multiple inputs and outputs. It also saw the emergence of new techniques such as frequency domain analysis, root locus method, stability analysis, and frequency response method that could solve various control problems. In industries, increasing labor and equipment costs and development of high-capacity, high-performance equipment and processes had rendered chemical plants uneconomical without automatic control. At this stage, feedback controllers were added to the plants with little real consideration of or appreciation for the underlying process dynamics. Rule of thumb guidelines and process experience were the only design techniques, which were deployed on a case-by-case basis. After 1955, rapid advances in computer science and artificial intelligence revolutionized automatic control research. It introduced new paradigms such as state space methods, neural networks, fuzzy logic, genetic algorithm, reinforcement learning, etc., that can handle nonlinearities, uncertainties, constraints, optimization problems, etc. This period also marked the third industrial revolution, known as digital revolution. In the 1960s, chemical engineers were experimenting with new developments in dynamic analysis and control theory. Most of the techniques were adapted from the work in the aerospace and electrical engineering fields. In the 1970s, rapid rise in energy costs urged for effective control applications, which are referred to as advanced control systems. The design and redesign of many plants to reduce energy consumption result in more complex, integrated plants that were much more interactive than before. Digital control systems were introduced in this decade, allowing for more precise and complex control. The decade following this period saw development of methods such as model predictive control technology, as well as hardware transition from pneumatic to analog or electric to being microprocessor based. In 1990s, integration of control systems with computer technology led to the development of supervisory control and data acquisition or SCADA systems. At the end of the century, wireless technologies radically changed the communications paradigm which enabled Industry 4.0. Today, process control continues to evolve with the use of advanced technologies such as artificial intelligence, cloud computing, the Internet of Things or IoT, as well as cyber-physical systems. This is the end part of this session. Students can gain more information in using these sources.